let's look the subtask tree. So there was basically two tasks, there's many steps, but they're practically two. The first one was just to look the Pyhäsalmi mine catalog and try to determine what are the dimensions of the deep ore body. The platform doesn't yet have too well and too advanced 3D capabilities, so we have not been able to put the geological model of the Pyhäsalmi mine's deep ore body and the geology in general there. It's possible, but we just couldn't done it yet. So the task was to look the catalog to determine the dimensions, and after that, it was to using the jet coordinates as a filter parameter to cut this deep ore body and its region in the three different areas in the upper, bottom, and the middle sections, and then to look how many events does it have. And as a second step on this one, then it was supposed that you refilter those filtered catalogs from these three sections and filter them in two parts using the time as a filter tool. So we can look that first. Yeah, as usual, we need to go to the episode platform to get the access to workspace, and I already made here this practical session 4 folder and subtask 3. And I already fetched the Pyhäsalmi mine catalog from the episode page. So since we don't know the actual coordinates of the Pyhäsalmi mine, the deep ore body, we need to go and look the seismicity, as I gave you a hint that most of the seismicity is around the ore body. And one way to do it is to there is a 3D plot basic capability, but it's very slow. But you can plot 2D and to see that how the seismicity is concentrated. And I'm going to plot the x-axis using the values from JIT, the mine coordinate jet, which is the elevation from the surface, and for the y-axis I'm giving well, it could be y or z. Let's just put z, and we can plot this. So now we can see that the elevation is here on the x-axis, and then on y-axis there is now the coordinate x. This can be done many ways. I just put it like this. With this, you can zoom a little bit more, and it's quite clear that there's some events in the surface, and but most of them are concentrated on this area. And by looking the episode main page, you see that it is like potato-shaped, this ore body. So it's most probably this part of ore here, but and these events over here and here, they are associated already on the steep tunneling. But I think that somewhere here could be reasonably to guess that around 1,000 meter, 950 or so would be the top of the deep ore body. At the bottom part, there's a lowest at the minus 1.6 kilometers. If we look at the jet coordinate, I think it's something like 1.45 kilometers. Well, I know that it is there, but the task was here to estimate. So 1.4, 1.5 could be a very nice guess. for the dimensions. Then the next thing would be just using the filter tool, which I already had the filter tool here, but it can be found using the application and catalog filter. But I'll use here the one I already have. Then it's implemented and then it was supposed to filter against the jet or the elevation. You could also use elevation here if you have looked at it's totally okay. But I used in the inspection the coordinates from the mine coordinate system, so I'm using the jet here. So I think that the bottom was somewhere something like that, and since we determined that most probably the highest point of the ore body, the top part, would be somewhere at 1000 meters, so that's 500 meters in a vertical direction, the dimension of the ore body. So we just need to divide this in 3 parts. So I think that we could put something like that the lowest part would contain everything from minus 1500 meters to minus 1350 meters, so 150 meters. And we just run it. So we have a new catalog which contains 450 events. So not too much. If we remember that the original catalog holds more than 7,000 events. Then at this point, you see this is the new catalog that was created here. So I would say that you should, if you are using the same application, remember to rename it. Something like that. Then if you're using the same application, you don't lose that one. I already did the other filtering. So if we look at the middle, I need to look at what I used. Okay, I've been using a little bit different sets here, so it's I think we need to do that again. So that was now the bottom part, and if we then take the 350 and we go another 150 meters. Sorry, like that. Then we have the next vertical slide of the catalog. And okay, this already have a more than 4,500. So majority of the seismic events are between 1.2 to 1.35 kilometers at depth. So this is quite clear. And then the last one, what you have to use would be the most top part, which in this case would be, well, we can just put it like that and take the remaining 200 meters on that one. And these have 1.8 thousand seismic events. So we can say that, okay, the middle section of the at the Pyhäsalmi mine deep ore body is the most seismically most active area. And this was just to be demonstrating you that you can this way filter different areas and look how much the seismicity is changing within these 6 months in the different regions of the mine. It can be some other industry, those wastewater injections, and or water reservoir compounds. The main idea here is to see that the seismicities actually have different places, and if you would have making this in more discrete sections, like 100 meters, you probably could have isolated the most seismic area with more easily. But this is just sliding things. Okay, so then it was asked that you should look that is there any timely changes in this in either on all of these sections what you have made. And let's take that. I think let's take that middle one what I already made before, and this time it had this around 3,000 events. And you can see that the time range is from start of the episode, which is October 1st, 2010, and the last part is end of March 2011. So this is half a year of time period in this episode. So we can use this again in application, catalog filter, and to do a refilter on this in this catalog. And of course we could use the filter both the depth or the jet component and the time range on the same time. It can be done. But now we are having all those events what we had in the filter catalog, and we just use the time to change it. And we will take the first half of the episode, which is from October to end of the year. Like that. Actually, I think I need to put it into this, not December. Oops. It lost it. Well, that's all right. Now we're back here. So I will just take January 1st, 00. So it's taking the last day as well. Then we just filter it and look more. So the first half have 1.2 thousand events. So the latter part have to had more than that, 1,700. So we can say that the beginning of the year 2011 at the middle section is more active than the end part of the year 2010. And to further correlate this, next step would be to look how is the industrial activity, the mining is, how it's going on at the Pyhäsalmi mine. We have this mine fronts and the start date of that, so we could look that, but it wasn't asked here. So this is very simple way to evaluate the seismicity and the time chronicle and the spatial correlation between different sections of the mine. So this is what you were asked to do. I'm not going through those all because I think that you got the general idea from here and can test the rest of yourself if you haven't. So we can go on the second part of the subtask. And the second task was to look more at the Pyhäsalmi mine's catalog and to make some other statistical analysis on that. First of all, we need to make this completeness magnitude estimation, which meant what we talked last time, that most of the statistical analysis methods are assuming that you will know and have observed all the seismicity at the area. But like last time discussed. It is usually the case that the smallest seismic events, you can only see them if they are on the right place against the seismicity network. So most probably you don't see the most smallest seismic events, or it is impossible at least to localize those. So we need to leave those out of the analysis. And the completeness magnitude estimation is usually done for this in the beginning when doing any group seismic analysis. So this again is using the catalog. So we can use the whole Pyhäsalmi catalog, the original one, and using the application. Completeness magnitude estimation over here, like that. And this doesn't actually have too many of input parameters. There's ML and then this synthetic datasec. It kind of make many versions of the catalog to increase the statistical reliability on this application. So we can just run it. All right, so this actually is estimating this in 3 different ways. One is this goodness fit test at 90 or 95% confident bounds, which means that with these bounds, it's kind of that it's trying to fit all the frequency of the events on this Gutenberg Richter relation. And with 90% confidence, it says that all events that are minus 1.2 on local magnitude scale can be seen with this seismic network. And the ones that are below this value are starting to lose coherency. And you can see it actually in this plot. This is the fit, the red line over here, and these are the cumulative number of seismic events. So you can see that it's actually quite flat over here. So there's not too many observations on the smallest seismic events. And then as the numbers started to decrease, it means that most of them have been seen on different magnitude levels. Okay, then there's this 95% confident bounds, which makes it more strict on the statistical point of view. So it would only say that all events above this minus 0.9 of magnitude can be seen. And then there's this maximum curvature method, which also is fitting the line. It says 1.1, minus 1.1, and the minus 0.8 with this modified goodness fit test. We are going to go forward with this minus 1.2 just to get a decent number of the events there. So this was this majority, or the main thing what you will get from this application are these values over here, what you can use in the group analysis applications, what we are going to use next. Then we can use, I think the next step was to estimate those distribution functions, the source size distribution functions. And again, the catalog is the input file. It automatically chooses the magnitude column, and then it asks the minimum magnitude what we want to use. And our complex magnitude estimation, what we had just made, we enter that value from that one. so minus 1.2. We can use day, month, or year value. Let's use day. This is used for the computation, including times. So you can see it from the plot. And then there's this magnitude distribution estimation method. There's 4 different here: unbounded Gutenberg-Richter model, upper bounded, so it kind of gives the upper bound limits what for the analysis, that what is the most uppest magnitude that can be resolved using this Gutenberg-Richter magnitude distribution functions and relation. Then there is non-parametric kernel and non-parametric kernel with the upper bound. But we are using in this one, this unbounded Gutenberg-Richter model, because it's a simplest one. Then we need to put plotting for the magnitude. So obviously the minimum magnitude what we want is this minus 1.2, and the largest one is 2.2. You can see it from here. And the step is that what is the magnitude step limits, and let's put the 0.1 here, so it's showing the value for every tenth of the magnitude steps. Right, and this is quite fast. It just calculates the different parameters here. So for the whole dataset, it gives this p-value of 1.2. And for the p-value, I'm sure that you have discussed it with Elena at the lectures, is this kind of one of the parameters in this Gutenberg-Richter equation. And it can be kind of describing that what is the relation or the proportion of the larger events, let's say magnitude of 2 versus magnitude of 1, that if this would be close to 1, it would mean that there is more or less this 10 to 1 on this proposal, that every event that is magnitude with 3, there is 10 times more on the 1 magnitude scale, less in this case the magnitude of 1. So it's kind of giving information about how much how well this Gutenberg-Richter relation is working. And mostly in mining, it usually can be 1, but usually it's something else. And the changes in this p-value can be that our observations are incomplete, so we don't have seen every single event. This can be tricky here because we are quite close at the lower margin. You can test yourself if you put some higher value here, like 1, or for instance. Then what else this F magnitude round of interval 0, which is quite nice. It does mean that there is not too much of a statistical error in the solution what we had. And then this mean activity rate above completeness magnitude and the mean activity for all events. So this is the activities. How many events we are having per day over this the minimum magnitude what we said, and down here is this which contains all of the events. So you can see that approximately more than half is above this minimum level. Then we have the probability density functions and cumulative density functions, which just means that what is the probability on certain different magnitudes. But we don't have to go on this. It kind of tells you that the smaller or the higher the probability density function is, the more probably the event on that magnitude on occurring during at the mining site is. And as we can see that the probability for the largest events in the Pyhäsalmi mine is quite low, which is of course the case. And the cumulative magnitude is just saying the other way around, so it just cumulatives the probability. So when all the events are included, then the probability is of course 100%. All right, but this application gave information about the activity and the p-value, and these parameters can be then further used in another applications. And it was asked to use these properties in the stationary hazard, exceedance probability, maximum variable magnitude, and mean return period. And it was then asked that what these are telling you about the seismicity at Pyhäsalmi mine. All right, so this sshparams.mat is the file that contains those information, and we can use that in application. And there is only these three applications where you can use this file as an input file. So let's use the mean return period. And for the mean return period, it means that now we are calculating the time, I think it's in days, what it takes to certain side of magnitude side event to occur. Well, let's start from this 1.2 and end at 2.2, and step would be the same every 10th of magnitude. And let's run. And this is practically used by the p-value. And this just gives this plot as an output. So this have two scale, the magnitude with this interval what we set, 0.1, and then the mean return period in days. And it's 200, 400, 600, and 800. So it's a lot. And as we set this one -1.2 as the lowest magnitude what we want, mostly because the reason is this, because we only use this events to calculate the source size distribution functions. So the magnitude of -1.2 would return every 0.05 days. So this means that there is actually happening quite many of this side of magnitudes daily at the Pyhäsalmi mine, which can be, of course, looked if you would filter the catalog in a certain magnitude, this -1.2, and then you would see how many days there is in the catalog and how many of these site event you have, and you probably, if you would calculate that how many occurs per day, then you would have the number which is inverse of one of these. So it would be that one inverted, how many of that is something like 20 per day. Then for the larger events, let's say 0. So magnitude of event of 0 magnitude would be occurring like once a day, a little bit less. And as larger events we go, this mean return period starts to increase. So magnitude 1 would happen monthly, and event of 2 would happening in every once a year, and event of 2.2 would happen every 2 years or so. Now, if you would look the catalog, you would see that okay, there is not too many of events happening on this larger scale events. which means that the probability on this one is not that good that it is for the magnitudes, the smaller magnitudes, because the number is larger and there is much more on reliability on the statistic on that way. But it shows that with a good large catalog, for instance, for Pyhäsalmi mine, if we would put on the catalog all of the events what they have seen during the last 10 or 20 years, I think that we would get much more detailed and reliable information about the distribution here. There's some options here that we can actually use. Oops, not that one. We can have a logarithmic scale, and you can see that it is mostly a straight line if we apply a logarithmic scale on the y-axis, and you can see that this is mostly because of this kind of the fitting is kind of put it in this Gutenberg Richter relation, which is supposed to be straight line if we are using the magnitude, and our p-value is close to 1. So this gives you information about how frequently certain size magnitude is occurring. We can look another one. Let's look the maximum credible magnitude. So I'm using those SSH params as the input file over here. All right. Guess that nothing. All right. Ah, yes, I think I need to use. Okay. I hope that this is still working for you and you're hearing me, because I seem to be suffering a little bit on bad internet connection here. I guess you are still there. All right. And use that in the maximum credible magnitude. Okay, now it's working. So this uses the same input parameters, but we are looking at in a little bit different point of view. Now we want to know that what is the largest event that is most probably occurring on the certain period of time. So if our time period here is the length is days, starts, end, and step. Let's put that our start would be 0 and our end would be 30 days. And our step would be 5 days. So it gives us the period of length in days and the maximum credible magnitude in the y-axis. I think that the 5 is too less. Let's just put 1 day over here, so we can kind of look that if we are increasing the time for daily. Okay, now it looks a little bit more understandable. This is change the charts type, by the way, so you can make lines or spline lines to help you to visualize the changes in the curves, even though this is quite clear anyway. So we have the period of times. We started from 1 day. Of course, it can't calculate for the 0. For the maximum credible magnitude for 1 day would be minus 0.1 of magnitude. And if we wait 2 days, then the largest would be 0.2, 0.3, 4. Well, now it's just going like that. But if we look at what is the period of time if we want to see, or if we expect it to see an earthquake in a magnitude of 1. So we can go and right over here. All right. So over here we have 1, or maybe this is just a rounded 1, but it would say that every 20 days we would have this magnitude event of with size of magnitude 1, which is, I think it was quite similar result that we looked in the mean return period, in the mean return period in the previous application. So this kind of thing gives us the information about the maximum magnitudes what we would be expect to see based on our history at the mine. And especially when we have more data, like 5-year data, and we are expecting to see that the operation at the place is more or less the same. For instance, at Pyhäsalmi mine, they extracted the ore in different parts of the mine. They didn't go that in an order that they would start from the bottom, or they would start from the in the highest point of that ore body, but they did take that from different areas of the deposit. And the reason for that was that if you kind of give some time the rock mass to creep, so it doesn't necessarily collapse when you are going to extract the ore on the same area. So when the operation is more or less the same, then this kind of analysis can be used that when you are expecting to see the credible magnitude, the maximum credible magnitude at certain area. We still had that one application, what was called the exceedance probability, which means that in that one you are going to input the certain magnitude, and it will give you the probability how probably it is that it will occur during 1 day or your time unit. But you can look that yourself. All right, was there any? All right, so what this can tell about the magnitude and the events and seismicity at Pyhäsalmi mine, it tells you that the largest events, the occurring days are most probably, based on our catalog, longer, but there's a frequent number of the smaller events. And those smaller events, of course, they can be hazardous if they're in the wrong place as well. Okay, so that was more or less subtask 3. And let's go into another part of the group analysis. Last time there was one group analysis that I wanted to show you, but we ran out of time. So it is this seasonal variation in the seismicity. And for this, we are using a certain episode. We go to the episodes, and here is this Gisos-Serville, what we talked about last time. This is the main page. And this was about the salt extraction, and then there's occurring voids, which can result in the collapsing of or caving in this kind of a situation at France. They placed sensors there for a year and a half, and during that time they observed the different seismic events there, and they range from -2.9 to 1.4 range. And there's actually 2 catalogs. in this one, the one which have determined the moment magnitude, 22,000 events, and then all detecting events, but we are interested on that one, which is having the moment magnitude. So we are going to get that one for this next application. So it is that one, and we add this workspace. And I already have made this practical session 4 and group analysis subfolder and a seasonal subfolder where I'm going to put this one. I'm going to show it going straight to the workspace, and then we have it here. So we can first look the catalog. So such as we looked in the, here's the moment magnitude. So we can look to the histogram first from here, the plot and histogram, to show the distribution of those events. All right. So we'll see that there's quite a few larger events, and then there's a few on the smaller events. And based on our experience now, we can say that definitely the line that where we can see all our events is somewhere here. So if we would make a components analysis for this catalog, we would get something like -1.3 or -1.2 as the lowest number of magnitude of events. Those above we can all see. And yeah, so there's quite a lot of numbers in this catalog. What else can we look for the catalog? Well, we can have some certain things and the parameters what they have calculated here, scalar moment and the P-wave energy, corner frequency from the spectral analysis, and source radius, apparent stress and static stress drop, which describes that how the event has occurred and how much energy and movement there has happened in the during the earthquake. But we can now look for the seasonal trend variation, and again we use this catalog as the input file, and now it is the seasonal trends, time correlated earthquakes and seasonal trends. And this is the application what we want to use on this. All right. So here we are, and this looks that it has many of the different kind of parameters, and for the site name I'm giving this res. I think that it wants to have something on here. And then there's this magnitude column, which is usually takes automatically if there's none other. Chosen depth or elevation. We need to look into the, I will open the catalog with the different windows so we can see that whether it had depth or elevation as a existing parameter. And once you come here, you can see that there's the jet coordinate. There's elevation, but there's also depth. So you can use either one of those. So let's use the elevation from sea level. Latitude range, longitude range is usually taking all the events from the catalog, so they are automatical. Elevation range from for little less, little below the sea level and something like 150 meters above that. That's the range of the events on this catalog. Time range, we take it all. And then there's the magnitude range from -3 to 1.4. And number of samples, 1000 minimum 100. here is 1000, it can be 10,000. And this parameter here is something, if we put it this one, this is the number of the reshuffled catalogs to be stacked as a superposed epoch reference, which means that it kind of make this synthetic duplicate versions of the catalog and reshuffles it to make it more statistical stability for the dataset. It doesn't distort the catalog too much because it kind of duplicates it. So every proportional is still the same. Then the size of the bins, which has monthly, daily, and hourly. Let's start with the monthly. So then we can just run. There is actually that it might not now proceed because, yeah, unrecognized function or variable step. And this is because that our magnitude range here is too small. So we need to use that completeness magnitude estimation more or less. I think it was something like that. Oh, sorry. This is more strict on this magnitude range. It actually can be that we still need to decrease that. Okay, it's still that one. So let's decrease it even more. It kind of uses those which have a decent number of that. Okay, now we got something. All right, monthly stacks. So this application only produces an image, and the image, the x-axis is the time axis in this one, and what it contains is it's based on what you did select on here on this size of the bins, and now we select the monthly. The y-axis here is giving you monthly seismicity between that magnitude range, which shows us that the most of the seismicity has occurred during February to April. And as we know that there's at least 2 of the Aprils here, but it kind of gives the average on the time. So this gives us that, okay, so most of the action or seismicity has occurred to this time. Okay, this gives us the seasonal trend over a year. And it tells us when we compare it to the industrial activity, we can easily make some monthly correlation. I will try to put that a little bit lower, something like -0.6. Does it work? Oh, it still works. Okay, good. All right. So I decreases the magnitude range to have more data in this analysis. So let's say take the daily for size of bins and run it. And again, we will get an image here, which now gives us the daily statistic. And the daily days are here, the weekdays from Monday to Sunday. Okay, this tells us a little bit different. So it says that the most of the events are actually occurring during Wednesday and Thursday. Then it's starting to little bit taking off during Friday and Saturday. So what could we say up on that one? We would say that since the working days are from Monday to Friday, I have to say that I'm not the expert on this industry, but I think that the most industries are working, especially these ones are most active during a week time. They still have operations during weekend, but it's less. And this would say that okay, they start the operations, mining operation or whatever they're doing. On this one, they are extracting the salt. they started from Monday and Tuesday, and the seismicity is starting statistically to increase. And this would say that there is some delay in the seismicity versus the industrial activity. And during weekend, it's starting to decrease. And then when we're starting things next Monday, it's starting to increase again for the mid of the week. So there's a definitely trend here. There was one more thing. We can put hourly, which gives us another window here, a number of hours. So this means that it gives you the number of hours, how much it's going to put in one of the stacks. So I'm putting here 3, which defines the our day in these 3-hour sections, like that. So it means that there should be eight different time windows during a wind. Okay, so we got this kind of results. So it was seen that the most, by statistic, the most quiet times based on the hours would be during the midday, and the most active in the late afternoon and the morning time. So in this case of industry, which is not so familiar to me, I would say that they are starting to work in the day shifts, and but the majority of the events are actually happening during nighttime. So it's probably that they are injecting or collecting things after the work days or after the preparations, and that then the seismicity is happening as they started. But this is function of geology and of course the operation of the mining operation, as well the rate what they are doing, the industrial operation. For instance, in mining, if you mine out more material or use more frequently explosions, of course you probably will break and inflict some altering stress in the rock mass more frequently. So it means that your seismicity is of course increasing most probably. Yeah, so this application gives you the timely correlation of earthquakes. As we saw that first we looked at the spatial correlation or differences using the subtask 3, and this one gives us that is there any timely corrected earthquakes, correlated earthquakes in the operation. And this is application that you're going to use in this practical exercise work using the Pyhäsalmi mine. And I think that it's actually much clearer results than this one. Okay, so that was the seasonal earthquakes. Then there's one more application I'm going to show you. I think that we can actually copy that. So copy that file to the seismicity area subfolder. And I think that I can use this as an example here. So I'm going to use, now use this in the application called complete magnetic estimation. So this is the basic first, and I'm just going to run it so that we can get the idea what is the minimum magnitude that we're going to use in the following. And it looks like that is this one minus 1.2. So it looks a little similar than at the Pyhäsalmi mine. So -1.2, we know that now, and then we are using the catalog in another application called time-dependent hazard in selected area. All right, and here's the map on that. So you can see that there's a city of Nancy at France. And most of the seismics on this episode has occurred here. I think I kind of showed that. You can see that these events are mostly in grid, and that is because that they have just, when they have located the seismic events, they kind of have made it in the grid. And so seismic events are in gridded that they can see that what section is most seismically active. If we would put the satellite, we can see that there is those cave-ins, what we have seen, and during this time, only this portion have been active. Yeah, this application, this time-dependent hazard in select area, this is an application that is actually using those smaller applications that we have already used. This source size distribution functions, and then those stationary hazard functions as well. But this kind of mix this with the timely correlation and looking to how much the time is affecting on the observations. So practically is stacking those analysis into one application, so you don't have to make them using the different step on your catalog. So for this one, we are using that -1.2, and we are selecting all the events. You kind of have to select all the events in this episode and the other episodes as well, unless we would like to select only portion of the, let's say that you would have a clear difference in the place, so then you would use this kind of draw circle or rectangle or polygon in the map and select these events using like that. But we are using all, and it's only happening on, it can be happened either using these ones or selecting all here. Then what we have certain parameters to put. The first one was this minimum magnitude, what we use this completance magnitude result. Time range, we want to look the whole time range of this episode, so we leave it like that. And then there's time unit, and this small info buttons, if you put it here, you can see that it kind of unit that is used for the computation, including time. So it's kind of showing some days. It can be day, month, or year, but let's use day now. As you can see, there's this magnitude distribution estimation method, unbound Gutenberg-Richter model, the same that we used in the source size distribution function application to have determined the p-value and the activity based on the catalog and the frequency of the different seismic events. Then there's a method to creating time windows. There's two options: constant time period or constant number of events. I kind of, you can actually use either one of those, but it's a little bit different point of view. Constant time period, you kind of are interested on a constant time periods. It means that if you want to know that how many events is happening a week or what is your week statistics, then you would use this. Then the other one is constant number of events. So it kind of makes the time windows, how it's going to analyze your dataset based on the constant number of time events. So if there's 100 events for 1 week, and for the second week there would be only 50, then it would make your, and you want to use the number of 50, then the first week would be split in 2, and the second week would be remaining as 1 full week, because we want to then have a certain number of events on each of the time windows. But let's use the constant time period now. So then there's the next row, which says the time window time step, which is days, and the window size, which is also days. And the window size is that it's kind of time period what you want to look. And I want to look, for instance, 14 days. This is 2 weeks time period. How is the seismicity during 14 days? Now, the Windows time step means that it actually going to use this window size, in this 2 weeks window size, what we have inputted here, for the whole time period. And it's going to go this all through from the beginning to end using these 14 time windows. And the window step is that how fast we want it to move through this time range. So if I would like put 7 here, it would make an overlap of 1 week between 2 time windows. If I would put 14, it would mean that it doesn't put any overlap between the time windows. But I usually put some overlap, like half. So it kind of gives you more information about how the seismicity is changing during a time, so that there's not too many large variations. From the results, you can see this maybe a little bit more clear. Then magnitude. This is used for those stationary hazard applications. So let's put here a number of 0.5 and the period length for exceedance probability. And this is the period length is actually using this day. So we're giving here 7 days, for instance. And then we just run it. All right, and here we have, so based on these settings, we have 48 time windows created. So there is, starting from 2008 March, the first time window starts there. And if we click this show details button here, we can see those time ranges. So the first window started from the initial day and it's lasts at 14 days. The second time window steps with the 7 days from the beginning of from the previous time windows, which is March 13, and it remains this 14 days and so on. And then here we have number of events. And you can actually see that there is a number of events. So most active times we actually had in the very beginning of this episode. And then there's time windows which only have 40 or so events, which means that they are statistically not that brilliant to make. These are okay. But in the end, we have another large event over here in the very beginning, but I think that they stopped the measurements maybe a little bit too soon. Anyway, so now we have these 48 time windows, and for each of these time windows, the Gutenberg-Ritter modeling was done, and we got the activity and the p-value. And those are shown here on this window. I just like put the spline on, which is very useful when you have actually multiple crisscrossing plots over here. So the first one over here is the window number 1, 2, 3, and so on. And now we have time in the x-axis, and on the left y-axis we have the activity rate, which is this blue line over here, and on the right y-axis we have the p-value. So this is the time series what we have made using the source size disperse functions, different time scales, and we can see that the p-value estimation for all events is 0.99, so it's close to 1. But we can see that there is some variation between different data time windows, which means that there is changes in the seismicity and the properties and magnitudes frequencies in the between times. And you probably can see that in the activity, you can see that this is very highlighted, this first part. Of course, we saw from the windows that they had most of the seismic events, so it means that the activity rate most probably is very high. Then we can see that there's small variation during the other time windows. I think that you can actually zoom this like that, so you can have a little bit more view from those late time activity rates. So there's some activity times, there's activity rate 6 and then 10 and so on. These are not very large differences, of course, but they can be, it depends about the size of your seismic events, that whether you have a 6 or 10, it can be a really big deal. So you can see that the activity is increasing and then it's decreasing and again increasing in the last bit. Then the other line, this black line, is the p-value for each of the time windows. So you can see that they are mostly around this 1.2 or 1, but there is a few differences. For instance, we have this period of time here, the December. Okay, yeah. So the activity rate per day is like 2 events per day, so it's quite low. But then on the other hand, it's low all the way here. But the p-value have a major spike over here during this, especially this time window, and probably between the latter week of the time window here. So I would say it's an end of November to 4th of December. And in here, I think it's it kind of says that it is this November 27th to 4th that they have the most of the largest event there. And since we have the p-value spike here, it means that the proportion of the larger events is actually larger than this 10 to 1, what is usually in the Gutenberg-Ritter relation. It means that if we would have 10 seismic events on magnitude 1, we would have more than 1 on the magnitude of 2 events, maybe even more, because this is quite a large spike over here. But this kind of analysis kind of tells us how the seismicity is affecting in the magnitude, that certain magnitudes are occurring different times, and usually this kind of p-value spikes here. It means that there is more those larger events than compared to the smaller ones. Of course, you still have much more those smaller events, but the proportion is a little bit tilted, and you can see that there is some time variations between the time windows and this whole dataset. So this is the first part of this application, giving you information about the activity times, and then of course the p-value. And then we have two things here: return period and exceedance probability versus time. So this is the same that you actually saw, what we did, those stationary hazard applications. And again, this is done for those time windows what we had. And this is the return period, and what it returns the time that magnitude of 0.5 sized event occurs based on these different time windows. So we can see that the return period, there's a logarithmic scale. Does it look any good? Okay, it actually have one lot over here. So yeah. Yeah, I think I said this another way around. It means that it has actually less larger events than less larger events than the smaller ones, this size. And we can see it from here. So now that we have this logarithmic scale on y-axis, we can see that for the first time windows, the mean return period is 1.5 days for this side of event. And we can see that during the most active times, it's actually the return period is much less. That it means that as there's a lot more of events occurring, it's most probable that this size 0.5 size event occurs in a lesser time. And then we have a larger 30 days time periods statistically, a little bit variation here. And then we have this spike, what we saw in that this actually would be quite nice to see that how many events this time period actually has. So this is, well, we can look it from here. So time period was from November 27th. That one, okay, they seem to be 30 and 21 seismic events. It's not much, but it's still you can make some statistic on that, but I wouldn't be too sure about that. Yeah. No, sorry, it was that one. Yeah, 21. Yeah, not too many of events to make statistics, but more or less you can see that there is an increase on the prior and the later time channels as well. So maybe there is actually is happening something here that, or it's more quieter time as the activity gives us understand. Then the most at the end, we had this last time window, which is also 2 weeks, which says again that in this seismically active period of time, the return period of this event size is quite low. Then we also have the exceedance probability, and this was the one that we didn't go through in the subject 3, but we can go through here. So again, we have this 0.5 sized magnitude as selected magnitude, and this gives the exceedance probability, that the probability during these time windows, that how probable it is that this sized event will occur based on the statistics. And for the 4, 5 to 6 data time windows, the probability is quite high, almost one. Well, here it is 100% on these ones, and it means that based on statistic, this will happen in every, I think, what was the period length for exceeded progress. So it's 7 days. I used half of the time windows on that one. So during the 7 days time period, based on those time windows, it means that the 0.5 magnitude is occurring most probably. But then there's variation that there are those more quiet times. For instance, that one what had this b-value spike, it says that it's very unlikely to occur during a week, this size of a seismic event. But there's some variation on the or during the period of time. You will be doing this kind of analysis for Pyhäsalmi mine also. So that was the last group analysis applications I would use, show to you, and I think that maybe you got a general idea how to use it on this one. Of course, like always, there is this user guide, which gives you even more information how to input the parameters.